Okay, good morning, or I guess now it's afternoon, everyone. Second lecture day for this class. Hope people are having not too much trouble so far starting remotely. I know that Moodle had issues and Zoom had issues, and I don't think that there's any more platforms that can have issues, but on the bright side, that means that, what else could go wrong? So first, I'm going to just go over briefly before I start the Zoom etiquette, which hopefully everyone got a chance to look at, which is just mainly 3 points. So first is to just make sure that your mic is on mute if you're, unless you're going to be actively speaking, such as to ask a question. This is just to reduce background noise and whatnot. Second is that if you want to ask a question, just pop in the chat and you can say that you have a question, then I'll call on you, or you can just type your question there, up to you. And then lastly, just if you have a webcam, I ask that you do keep it on just to keep engaged. The hardest part, honestly, for everyone coming in as a first-year student this semester is going to be working remotely to keep engaged. You don't have the peer pressure of you're in a classroom, everyone else is in the classroom, you kind of have to pay attention and stuff. And so that doesn't exist anymore. And so, the best way that we can try to do that is to try and just be as interactive as possible. Okay, so that's all for Zoom etiquette. So I'm going to go ahead and share my screen here. If anyone would like to follow along, of course, I'll be sharing the screen to do it, but if you would like the actual presentation yourself, you can check the course website, which I linked, or I can also link the lecture page here in the chat. And then you can find the PDF here. And I'll try to post these before each lecture. So welcome to the CS program here. This is going to be your first year seminar. And the topic that I made for this is applications of computer science. And this was a topic that I had coined in a Unix course that I had taught. So I've taught a couple courses. And so in a Unix course at the end, because it was mostly first year students, I decided that since there was extra time, it'd be a good idea to see if people wanted to cover content that is covered in this course. And the general consensus was that it was very helpful to their degree and to their success. And so hopefully you'll be able to find the same here. But basically, first year seminars, they are designed to introduce you guys into the CS program. And start integrating you into this environment that we offer for you. And so in particular, this topic, right? So may be surprising, of course, but there are many applications of computer science. Hopefully, you're doing a CS degree for one of those applications. But, I personally know people, for example, that work with robots in healthcare in Japan. I know people that work on the backbone of the internet at Microsoft, right? I know people who work for SpaceX who design systems for space shuttles, right? So like all these people, in fact, roughly half of them came from UMass that I know personally who went there, but all these people came from the same background as all of you are going to come from, right? And so you can really choose what you want to do. There are limitless opportunities within not just CS, but STEM as a whole. And so the question that I sort of try to pose, which most of you aren't going to know the answer to yet, is what do you really want to do with your degrees? All that we're really sort of told going through the education system is, well, you're going to go to middle school, high school, and then you're going to finish, then you're going to go to college, you're going to get a degree, and then you're going to have a job, right? You're going to start life. And what does that really mean, right? Like, how do you do that? And what job? Like, you may not have seen lately, but lots of people are unemployed, right? And so it's this big sort of question that everyone assumes that you know the answer to, and it's like you're drawing an owl and they're like, all right, make a dot and then draw the rest of the owl, right? Like, you don't know how. And so my goal here through this course is to help you to help place those dots for you to be able to connect them a bit easier, to find out not just what you want to do, but how to do that. Brief bit about me so that you just know a little bit more. So I'm a PhD student here. I've been in university for roughly 5.5 years. And I did my undergrad here at UMass, finished in 2018. I had a minor in math, and I've written and I've taught 3 courses excluding this one. So this one might be my 4th course in the CS program here. So I've done both industry and research work, so I can attest to both sides of that. I worked as a security engineer at Amazon. I worked as a researcher in Japan. in industry, and I've done a lot of academic research work. And I've taught most of the content that's going to be in this course before, twice actually. So hopefully we'll have a pretty good experience. I'm hoping to share the same experience that I had in those courses with you guys. So for this course, it's trying to do it a bit different compared to other first year seminars. So the typical way that first year seminars are laid out is that they pick a topic that's picked by whoever's going to teach it, such as brain teasers or machine learning applications or common STEM for the common good, computing for the common good, that kind of stuff, right? So they'll pick a topic and then they'll just sort of go across that for the whole time. 5-ish years ago when I did mine, it was on I think it was on Python, like machine or some data science stuff with Python, and I hardly remember anything from it. And so what I'm wanting to do with this is essentially provide a lot of different content and then have people rank and prioritize what sort of order they feel that content would be most helpful for them. So ultimately, you are going to be deciding if something's not helpful for you, why teach it to you, right? If something is going to be helpful for you and it's not included, then I should include it, right? So that's sort of the idea here, is that everything's going to change over time, right? Job market is going to look different from people who graduate in 2 years, from 4 years, from 6 years, right? Compared to now. And so courses should change with that. And that's the idea, is that this course should change to match your guys' needs. What I'm going to be doing is present a variety of topics and see what you all most want to learn about and what is going to be most helpful for you all. It's important that we only have 12 lectures outside of this one. And so it's not a ton of time to be able to cover these topics. So prioritization is going to be important. And to that extent, once Moodle is done dying, I will upload a survey to that that'll ask you guys to complete by Friday, end of day Friday this week. And that'll just basically be able to rank in order sort of the prioritization that you want for content through the rest of the semester. And it'll also allow you to put in, say, if you want a new topic that I didn't include, then you'll be able to include that and I can look into including it for you guys. But I will send out an email when this is up as well. So to go over a bit of the administrative for the course to get out of the way, so basically we'll be using the course webpage here as well as Moodle once it is alive. But course webpage, hopefully you had an opportunity to look at it. Basically a brief note again about this course topic exists. So I already covered the second part, but really what I'm wanting to do is I felt that the content that's included in this course wasn't really given to me nor to any other students who've gone through the program before. Yes, we have advising, but it's not meant to help you figure out, what sorts of tools you can use to improve your learning. It's not meant to tell you what sorts of jobs are out there. It's not meant to tell you how you become a network engineer, how you become a robotics grad student, right? Like none of that's really told to you, and you have to ask very specific questions to very specific people. So the idea here is that I want to convey to you all of those possible opportunities and how you go about doing them. But most importantly, I want to tell you how you should do the things that you should do while you're here to maximize your time and why you should do those. It's not going to be useful if I don't tell you why it's important and convince you that it is important. So that's going to be my job, is convincing you that these things are helpful for you. And so if at any point, right, you feel that these goals are not being worked towards, or you have additional content that you want to be covered in order to satisfy these goals, do send me an email or just bring it up during class. Either one is fine. You're more than welcome to use the chat for that. But basically, if you feel like it's not helpful, do tell me, because I do want this to be helpful. Okay. Grading wise, so there's going to be 5 written response sort of questions. They each count as like an assignment. I couldn't really think of a better word for them. But basically, you'll just have roughly 150 to 300 words you'll have to write once every 2 weeks-ish. You don't have one for the next 2 weeks. It'll be in about 2 to 3 weeks you'll have your first one. And basically, as long as you submit 4 out of 5 of these and you just meet that word requirement and you answer whatever question's being asked, then you get an A, right? Any less than that is like, 3 out of 5 would be a B, 2 out of 5 would be a C, and so on, right? But really, it should take no more than 15 to 20 minutes of your time for each one. It's going to be personal, subjective questions. Like, an example would be, for instance, hearing these topics, what sorts of fields are you interested in and why, right? Be something like that. regarding attendance. So I know that we have lots of different time zones, people, attending from different countries, and that's really cool, but it also presents the problems that come with attending online lectures. So I do expect that everyone attends these lectures if they can. I know some people are in different times, like I said, people may be in India or China right now, and if it is difficult for you to attend and still maintain everything else, then you can watch these lectures asynchronously. I do record, I have 2 sections for this class, and I'm recording both sections, and I upload them immediately afterwards online. And once Moodle's up, I will post the lectures there. But I'm also going to be modifying the course webpage later today to have those. So if Moodle doesn't come back up for a little bit, then you should be able to get them there. But those will be posted if you cannot attend, or if you have to miss one day or something, that's fine. But do try to attend when you can. We already went over Zoom etiquette, and then I don't really think academic honesty should be a problem here, but don't, I guess, copy and paste an answer from Quora to someone's life experiences. Talk about your own, and you should be good to go. Okay, so let's actually say, so does anyone have questions about any of this so far, any administrative stuff about the course, or does that make sense? If you have a question, you can stop me. Okay. And let's see. So broadly, the topics in this course are going to be organized into 3 main sections. Not necessarily in this order. Again, that's going to be determined after we survey. But one is I'm going to talk about several different fields of computer science. And each of those are going to have their own lectures, 1 to 2 per lecture. And that, talk about in a minute what's going to be in those lectures. But talking about the fields, so example is artificial intelligence, or networking, or computer security, or bioinformatics, or whatever, right? Tons of different topics. Then there's the actual uses of these degrees. And so that's going to include stuff like internships and how to get them, why they're useful. That's going to include how to properly build a resume, what should be on it. That's going to include information about coding interviews, which if you don't know about them yet, you will soon. That's going to include information about grad school, right? Do you want to do that? What kinds of industry opportunities are there out there? What kinds of engineering positions can you get? What makes the difference between you being a Google employee and say, making 120 a year, and someone working at like a government contractor making maybe like 80, right? What's the difference between that? What kind of differences are in those people? So whatever your goal is, basically, I'm going to cover all those to be able to match, right? And then lastly, there's tools for success. And this includes not just in the CS program, right? Like development tools or development environments, whatever else, but we'll also include things like organization, right? How do you organize yourself? How are you supposed to keep track of all your tasks when everything's online, and how you try to keep engaged and everything like that. And tips that I've kind of gotten over the years, right? But again, if there are other topics you want covered, feel free to suggest them. So I'm going to go into depth a bit explaining about these different topics so that you have an awareness of what's going to be in the rest of the course, and have a basis for voting in this survey. So when I'm going to be covering a field, which I'm going to just kind of introduce a bunch now, what I'm going to do is I'm going to start the area, I'm going to start the history of it, where it's at today, and what I expect it to look like in the future. Also what the job market looks like, how employable is this particular area, right? Also going to demonstrate fun examples of the applications of this. So an example would be, I was going to, for computer vision, put together a small program to learn how to play Mario, right? Like old school, like 1980s Mario. And then I'm also going to go over the course progression here at UMass, so that if you want to actually work in this field, or if you want to see if this is for you, here are the courses that I would recommend taking. Right. So to introduce you to some different fields, the first one, which is the most buzzwordy of all, would be artificial intelligence, as well as machine learning. And these two terms are kind of just thrown around a lot and used synonymously. But essentially you have artificial intelligence, which is this big cloud, and it's about creating machines that can reason on their own, right? And usually the basis for this is search algorithms or game theory, which I'll cover later as well, and some sensory inputs. So like sensors that, maybe vision sensors like webcams or microphones or buttons or potentiometers or accelerometers, whatever else, right? And an example, right, is that you want to create a robot that takes visual input, maybe it's infrared, and uses some search algorithms to be able to find an optimal path. So from point A to point B, You want this robot to be able to navigate around obstacles and whatnot, right? And that would be a combination of search algorithms to do that. And it's not actually that difficult, or it's not actually that easy of a problem, right? Because if you consider there's a lot of things that can happen. Things and, obstacles can move. There maybe is not a path that is optimal. There's no path at all, maybe. So these are different problems that have to be taken into account, right? And where that puts machine learning is in a subset of artificial intelligence. And really, machine learning is at its core. You take some input and you learn with or without human feedback to transform that into some output, right? And what that means is that really machine learning is function approximation. The most basic type, for example, is linear regression, which you've already learned, right? An example of a classifier that I don't know if you, I guess, learn in an AP course or something, but would be logistic regression. Like that's actually used in machine learning as a first, usually like a first model people try. And so an example, right, is that you would take some data set of millions of flu symptoms, and given a person's symptoms, you want to spit out the probability of whether you think they have flu or not, right? And that would be a machine learning problem, and the solution to that would be a classifier, right? So ultimately, the foundational thought really behind machine learning is that everything is modeled after some learnable function, and that function can be approximated through enough data. And that's why you always hear this like big data being thrown around with machine learning. It's because the more data you have, in theory, the more accurate your solution is going to be. Okay. So that goes on to computer vision and natural language processing, often called NLP. So computer vision is regarded as a subset as well of AI and is about taking visual input specifically. And you want to be able to identify objects. That's sort of the foundational idea behind computer vision. So an example is you're driving an autonomous car, or I guess the autonomous car is driving itself, and you want it to be able to detect road signs and read those road signs. That would be in computer vision. There's a really cool seminar that usually happens once a year here where it's all about computer vision papers. And it's like a 1-credit class, and you just go once a week and listen to the professor and guest speakers talk about computer vision and like their state-of-the-art research and stuff, and it's really cool. There's a lot of courses like that. Now, these also, it's usually, it's a subset of AI, and it usually uses machine learning techniques. If you've ever heard like the term neural network, we would cover that in the ML section. But an example is you take a bunch of transformations to an image, and then you want to extract this, you can see this 5 and 0 from it. You want to extract the data from it. And there's natural language processing, which is also sort of a subset of AI, and it's kind of like on the other side of computer vision. So it's about human language, right? Not just understanding it, right? But also being able to generate it in a natural sounding way. We've come a long way from when Siri was first sort of the first digital assistant that was introduced on like the iPhone 4, I want to say. And that was revolutionary at the time, right? But if you want to like look back at old clips, its voice sounded awful and not at all realistic. Whereas now, you know, you have all of these devices that honestly sound pretty decent compared to what they were, you know, 10 years ago. And, you know, you have lots of things that can be created like deepfake. You can transform one person's voice into another voice, right? Now, truly understanding the meaning of speech is a much harder problem than just being able to like translate speech to text or, you know, speak out stringing syllables together to generate speech. It's a lot of a harder problem. And so there's a lot of work being done in this space that's really interesting. One really cool area that I like is working on social media platforms. So an example is you've taken a bunch of human text on social media platforms and you want to determine whether it's politically left or right-leaning content, right? Like that's a very difficult problem, but it's a very cool problem because then you can determine, right, say if a bunch of Twitter posts are being taken down and people claim, hey, my content is being censored, my ideology is being censored. Well, you could use a combination of NLP research to say, actually, your content is not being censored any more than the others. We ran across a bunch of text. We ran these NLP algorithms to analyze your content, and your ideology is not being censored. Or it could find, yeah, your ideology is definitely being discriminated against, right? And so that sort of space is very cool. There's also a large space coming up now in NLP for misinformation, which is also really cool. So going on, you have software and reverse engineering, and I bring these two together as the reverse of each other, inverse processes. So software engineering is about designing, developing, testing, and deploying computer programs, right? Fundamentally. And I always thought, I guess, in my first year or so of undergrad, I thought that this was a pretty simple sort of area. I was like, well, why would you have a whole field dedicated to designing computer programs? Like, shouldn't that be within each, field? But it turns out that at that time, I hadn't worked on complex systems. There are many, many large problems that come when you try to grow a program, when you try to scale it, right? And fundamentally, you need some solutions to try and go along with those problems of scale. So an example, right, of something you may not consider. So say that you are tasked at, I don't know, JP Morgan or something, and you are developing an interface for a trading system, right, such that anyone can use it. Well, two problems that may not, be immediately visible to the eye, but definitely would come up in that development are, one is that you're working with high volatile trading systems, high scale volatile trading systems, and you need to make trades extremely fast, and a microsecond of processing time matters, right? So now you need to design your program super efficiently to run on like very small chips that can run, very fast, and an extra microsecond of latency to be able to do one additional if statement. That could be the difference between someone making $1 million and $1, right? Additionally, another problem is you're trying to design it for anyone, which means that you have to design it for the most basic of people who don't know how to use trading systems, but you also just design it for people who've been trading for 20 plus years, right? And want very complex things they can do in the panel. At the same time, you don't want an action to be too complicated to get to, but you don't want it to be too simple to get to. It shouldn't be simple enough to just trade $1 million with one button, but it shouldn't take you 30 buttons to trade $1 million if you need to do that very fast. So a lot of these problems can come up in the development of something like this. And that's why this field sort of exists, is for designing principles for answering these problems, right? And there's reverse engineering, which is the reverse. So you take some finished software and you want to break it down and understand how it works. This is most commonly used in security research. So an example is you find a malware and you want to reverse engineer malware. You want to break down how that works, right? So I taught a course about this that was very cool. And if you're interested in this, there's like, we have a bunch of courses here. We have a cybersecurity institute that's got a bunch of courses about this kind of content. And this is also like a very up and coming field, particularly because as there's more and more programs out there, you need to have more and more people checking to make sure things are secure. So an example would be like, government contractors need to be able to go and audit government software, or your contractor to audit corporate software, or maybe you're hired by Google to design whatever system securely, right? So part of that would be able to take on the role of a hacker, in which you try to penetrate into systems and then build them securely that way. So it's always good to know the back way, the reverse way, right? So moving into this space that's usually called theory. So there's three main spaces usually in CS that we refer to, at least at UMass, which is AI and machine learning as its own group. Then you have systems, which is like networking, security, sort of working with actual hardware. And then you have theory, which is everything left over that nobody wants to touch. So, because it hurts your head. So examples of areas in that space would be algorithms and data structures, which are put together because they go hand in hand. So at its base level, right, an algorithm is about developing some process that solves a problem, right? And algorithms get increasingly complex over time, which is why there's a field for them. You come across problems that maybe don't have solutions. You come across problems that maybe have solutions, but they're incredibly inefficient, right? And so you can't actually run them at scale. And so people in algorithms work try to solve those problems and develop processes for solving those problems, right? There's also a lot of qualities that you have to take into, or a lot of constraints that you have to take into account when you're developing an algorithm, right? What sort of system are you going to run this on? Is it going to run on a phone, or is it going to run on a desktop or an industry server, right? That makes the difference in how you can design it. what sort of disk space do you have? Is this something that needs to run on, a Game Boy Color and you have like a megabyte of space to work with? Or is this running on like, Facebook's data structure or Facebook's infrastructure and you have like, I don't know, infinite storage, right, in theory. And so really what this is about is finding efficient and fast ways to solve problems. And I always like to bring up this topic of genetic algorithms because I think it's very cool. And there's a lot of algorithms are actually inspired by what you might find in nature. And genetic algorithms is an example of that. So the idea is that you would take evolution and you try to use that in an algorithm sense. So you might take qualities of a computer program and just try flipping them on and off or changing them and seeing how that impacts the child program that's derived from that. And there's a lot of cool implementations of this out there. I don't know if anyone knows of like the video game Spore that was several years ago. Well, that uses genetic algorithms to like try and 3D model creatures and have them grow and stuff. It's very cool stuff out there. And there's data structures, and I say this goes hand in hand because fundamentally there are some problems that cannot be solved with algorithms if the data is represented in a certain way, right? And so data structures is really all about reshaping data into a new format so that you can actually work with it in an easier, more efficient way. Oftentimes, the solution to a problem will be to change how you represent your data and then use some algorithm that already exists to solve a generic version of your problem. So you just extend that a bit. And that's a very good way to try and go about solving problems that maybe seem difficult at first. And you'll work a lot with this kind of stuff in 187 and in it's 311 as well. So I, at the time, didn't find it fun, but in retrospect, find it fun. So maybe some of you find it fun, I'm not sure. But also within this category is databases. So, the problems change when you want to do data on the scale of a few megabytes versus several petabytes, right? An example is Facebook, for instance, 0.1% of its computing power costs several $1 million, right, for a year. And so if you can change how a database works to maybe shave off a transaction or two here or there, you can potentially be saving millions of dollars, right? So I have two more spaces to cover. So there's networking and cryptography. So networking is about communicating information. It's about the flow of information in some system. And one of the fun spaces that I like to think about in networks is reliability. So an example, right, is if you're transmitting data from Pluto to Earth, right? Maybe it's like some infrared laser or something, right? How do you know for a fact that the data that you sent from Pluto is the same data that you received on Earth? And, when you think maybe of a problem where it's just like, oh, you want to send data across space, so just use a laser. But there's a lot more to it, right? So there's 4.6 billion miles of space to cover. And there's all sorts of noise and interference that are brought in. And so, what happens if like it bounces off the side of an asteroid and or some radiation gets in, or like other infrared light messes with it and then it adds together? Or what if something blocks it temporarily and so maybe like a second of data stream is lost? So stuff like that can happen, and you need to be able to determine how to remove that interference. Same thing happens, simply put, on like a video call like this, right? I mean, there's a bunch of different networks at play here. Everyone has their own internet system. So how does it play if one person's video disconnects, right? How does the system learn to handle that? So those are all cool questions, at least I think. I talk about cryptography, which is, I think, a little bit less popular than it was today, or a little bit less popular today than it was a while ago, although I've seen some people switch into it because it can be a bit of a headache. But the people that I know that work on it are absolute geniuses. So the idea is that you want to transform data into some unreadable format and then be able to transfer it back optionally. Sometimes you don't. Good example, right, is that if you are putting a password in to sign in online onto a website, you don't want to actually have that website store your password in plain text, right? Because then if the database were leaked, someone could just go and take that password and then try it on different platforms that you use the same email for. And that's oftentimes how data breaches happen, right? someone or some website improperly stores your password. Someone's able to take that and then use that to log into your other systems. So if anyone's ever experienced that, that's most likely 99% of the time that's how it happens. Right? And I also bring it up networking because a lot of the times you use cryptography and networking together in order to solve those problems of reliability, as well as solve problems of security, right? How do you know that the data that you send from point A in USA is the same data that you receive at point B in Russia? You know, when you have maybe 20 different computers along the way that intercept and have to forward that along, right? How do you make sure that that's like the same data? So cryptography is used a lot in that respect. Then the last area that I want to bring up is robotics and then game theory. So an example, I have a friend who does this, right? He works for Amazon designing algorithms for moving robots around the warehouse, right? An example would be that, you know, you have a multi-agent path planning problem is what it's called, where you have multiple robots, right? Multiple agents. And they want to get from point A to point B, each of them optimally. But there's a bunch of obstacles in the way. Robots may be moving in between. So do they communicate or do they use like sensors to see where the robots are at? And then what happens when you have humans all walking around and stuff? You want to be very careful not to run into a human, but you also want to be as fast as possible with everything because this is, you know, a money is time type thing when it's trying to ship out packages, right? So very cool problems. I also know someone who works on like robots with medicine on the other side, and these two people would like never meet in their field. That's how wide of a field, you know, robotics can be. They work in Japan on elderly care with robots, trying to use robots to like help aid people with dementia and Alzheimer's, right? And there's game theory, which I think is also thrown a bit around as well, but fundamentally it's called game theory because it relates to kind of, I guess, wanting to win at a game, right? So the idea is that you want to make the best choice when whoever is involved is rational, which pretty much brings it down to humans and things created by humans, right? Like software. So an example would be, classic problem is called prisoner's dilemma. The idea is that you have two people who get accused of a crime, right? The judge or whoever, maybe the police, make them a deal and they say, all right, if one of you confesses and the other one doesn't, then the one who confessed, you're released, but the other one spends 20 years in prison, right? So it's like ratting out someone, right? If neither of you confess, you both stay quiet, you both spend 1 year in prison, right? Just 1 year. But if both of you confess, then you spend 10 years in prison. And these prisoners cannot communicate to each other. They can't plan out in advance and say, all right, we're both going to not confess. And if you confess, I'm going to kill your mom or something. You can't like, they don't get to communicate that, right? They have to decide on their own. And optimally, what would you decide on your own, right? You might think, well, clearly the best decision is for neither of us to confess because then we only both spend 1 year in prison. But at the same time, if they're not confessing and I confess, then I get to go free, right? And I don't really care what happens to them at that point, you know? But then you could think, well, maybe they're thinking the same idea. They're definitely going to confess in hopes that I don't, and that they get to stay in, and then I have to stay in or they get to leave and I have to stay here for 20 years, right? So this is one that has a very optimal solution, clearly, but it's actually still a hard problem, right? Because with the no communication and not really sure of what the other person's going to do because you're both rational, that's what makes it sort of, I guess, this game. And that's the idea behind game theory, is you're trying to, I guess, win at games when, or make these choices when agents involved are rational. Another example is chess, right? You want to play chess optimally. Well, there are billions of combinations of moves that can be done, right? To make a board end up at a certain position. And you have to think, well, if I do this move, what's the other person going to do? And you have to try and see maybe 4, 5, 6 turns ahead, right? At times. And so those can actually be pretty difficult. One that made news that was like pretty fun was AlphaGo, right? Which was this program that Google developed to try and beat people at Go, right? So any questions so far about fields? This is not, of course, everything that's out there. There's a lot more. bioinformatics is a pretty fun one. But I can't really cover absolutely everything. And what I wanted to do was just sort of cover the bases so that you have an idea going into this survey what some fields are about and what you maybe want to hear more about. Like if you thought something today was like, oh, that sounds kind of cool, I'd like to hear more about, what sorts of courses are there and maybe, fun things you can do with it, then, and how employable it is and stuff, then I'd be happy to talk about it. So any questions so far about these fields? Feel free to stop me. Yeah. Okay. So now I'm going to go over those other topics that I talked about and briefly about what would be in those that I would cover. So first is the uses of these degrees. So this includes things like internships, right? Where can you reasonably get internships at? How and when should you go about doing that? Why should you go for an internship in X company versus Y company? Should you go for one in research? Should you go for one in industry? Should you be a generic software engineer or should you go for like some other thing, like maybe a network engineer? What's the difference, right? What sort of pay are you looking for? What sort of experience are you looking for? You want to do one for like 6 months? You want to do one for 3 months, right? You want to go in the summer? You want to go winter? You want to go fall? Also, how do you go about getting those internships, right? How do you stay competitive when there's millions of other people trying to fill those same positions and there's only maybe like 100 to give, right, at a certain company? So beyond that, also talk about full-time positions that are available afterwards, right? Engineering positions, what kind of degree do you need? Do you need a bachelor's degree? Do you need another master's degree to get this type of position? What sort of pay can you expect from the position? What sort of hours can you expect? What sort of positions are out there in this field? Also research positions, what makes the difference between working at Facebook or working at a university? What makes the difference between working at Google's research division and working in an academic research division versus working in a research division in, I don't know, what's a research, like a government contractor, right? Also want to talk about grad school. So who is it for? Should you consider it? What sort of time investment does it take? What's the payoff from it? That kind of stuff, right? And I think it's important to also talk about resumes. How would you go about building a resume tailored towards any of these types of positions? When should you start doing that? Hint is you should start pretty soon. What sort of stuff should you put on it? How long should it be, right? I mean, resumes used to be just a one-page thing, but now there's like a ton of stuff you want to include on it, right? How do you actually get that on there and condense it, but still make it readable? It's actually a pretty hard problem. Coding interviews, in case for people who haven't heard of coding interviews, basically if you want to land a tech job, you need to code live for someone for a couple hours, right? And solve several problems. And usually there's multiple stages of this. First stage will be online. Second stage might be another one online, or it might be in person, right? Some jobs might have 1 interview, some might have 3, but they have very, very high failure rates because it's actually very hard to solve a problem in front of someone to write a solution in front of someone to a very difficult problem when you can't look anything up. You can't check if your syntax is correct. You can ask clarifying questions, but that's about it, right? There's a lot of pressure on it. You have to talk while you're doing it so people know your thought processes. So I'm going to be able to give tips for that and how you want to practice it and all that, because it's really just a skill you got to train. And I also want to go over tips, right? Job applications, what are some tips that I've gathered that would be helpful for this? Same thing for internships, right? And then ultimately, I think this boils down to things that you should start doing now, as in, this semester, and things that you should start doing throughout your degree and when you should do those things. When should you start applying for internships? For example, if you want to get an internship next summer, you should be applying in 2 months, right? And how do you do that if you've just started your CS degree, right? So it's stuff like that that I hope to try and address. Then I think that useful tools boils down really into 2 sorts of categories. So there's ones that are really for the CS program here, such as typesetting documents. So you want to be able to write better homework or something, or write a resume. Development tools, right? What's the difference between running something like Windows or running a Mac or Linux or something, right? How would you go about doing that? Why would you want to run one or the other? Code editors or development environments, whatever else, right? And then things like organization software, right? How do you keep track of all the homework that you have to do, the assignments you have to do, maybe you're taking like 6 courses online and you have to take all these lectures and they're all asynchronous and you watch them wherever, right? How do you keep focused on that? How do you organize all of that? Security tools, which I think is always very important and I like to go over. How to stay secure while you're browsing, all these different tools online and whatnot. And then general productivity applications, right? And different things that you have access to as a student here that you might not think about, right? Like you get Office 365, you get the whole Google suite, you get like unlimited storage in Google Drive, right? You get lots of tools that you maybe don't know about. You get free copies of Windows, right? Then for those of you who haven't heard of GitHub, those who have, but it's basically place that you would go and distribute software, right, that a lot of developers use. And so I'll show you this platform and different ones like it that developers often use to share code around. And so that way you can try and start getting integrated into the way that developers work and maybe be able to find a project that you want to work on. Projects are always very important to sort of have in your spare time to work on, places like seeing those when you apply to them. And then I also want to cover free stuff, right? Everyone likes free stuff, and there's a lot of stuff that you can get as a student, not just for computer science, but in general, that's going to help you throughout your degree. And student discounts that I think are worthwhile to use are ones that you may want to consider. Okay, so is there any questions on any of these topics or want something more elaborated before they'd be voting on it on Friday? And again, this lecture is recorded, it'll be online, so you'll be able to watch it again, or you can go look at the slides, I'll have those up as well.
You said you're going to go into this more in different meetings, but you said that you worked for your background in research and also in the field. Could you elaborate on that a bit?
Yeah, so about which part, sorry? The background here?
Yeah.
Are you asking that you want more elaboration on my experiences? Is that what you're asking, or?
Yeah, that's what I'm asking.
Okay. Yeah, if that's definitely something that you'd like interesting, and I will try my best whenever I teach something to sort of convey why I'm qualified to do that. So like an example is if I'm talking about different fields of research, or if I'm talking about, applying to a certain company, applying to like Apple or Google or Facebook or Amazon, right, for an internship, then I will definitely use my own post-note experience as well as experiences of people that I know. So in those times, I'll definitely bring that up when it's necessary and relevant. And when I think it's important to sort of convey that it's not just me looking stuff online, like this actually happened, right? And if you do want at any point like something that needs to be elaborated on more, or you feel like this doesn't make quite enough sense, just ask, and I'll be happy to elaborate on it. Okay, but I will try to get the survey up today once Moodle's working again, and then I'll send out an email to everyone, and you can check it out just sometime before end of day Friday, and it should take less than 5 minutes of your time. But you basically just rank and sort of order things, and I'll have a little formula that I'll use to say, all right, here's what people voted on and stuff. And I am doing your section separate from the other one, so each section has different people in it, so I want you guys' needs to be met, as your own group. So hopefully that'll be helpful. But otherwise, that's all that I have for today's lecture. I will stick around though until, what is it? At 2:15. So if anyone has any questions in the next few minutes that they want to ask me, whether it's about, hey, I'm considering taking this course, or hey, I have these two courses and I want to drop one of them, which one should I drop? Doesn't matter if it's like math or STEM or not. I can usually provide at least a little bit of insight on it. Then I'd be happy to provide input. So yeah, but otherwise, I will see you all then next week. And again, if you have any questions, feel free to email. My goal here is to make sure that you guys find this course helpful and you use it to help you succeed in the program here. I'd hate for you guys to make a big investment here and then not have as much of an output as you could have had because you didn't know how, right? I think that's the worst that could happen. So I want to try and prevent that. Okay. Yeah, so again, I will stick around for the rest of this, but hope you all have a good rest of your first day here, and wish we, be on person a bit, but I guess this is how it's going to be. So we'll make the best of it.